with the algorithm we have seen so far, and it is slow. If we have a number of add instructions in one block, and none of them is equivalent to another, then the problem is that only one will be removed at a time. So what will happen is that it will take the first add and conclude that none of them is equivalent to it, so all the others will be put in a new block, and then in the next iteration it will remove one more, etc. So this will result in a quadratic algorithm. If we instead can remove more than one instruction from a block, we can make a faster algorithm. Okay, and to do that, we will not let a block split itself, but instead let a block split other blocks. Okay, so actually we can start with a figure. If we have this block, and let's say that we have only unary operators, so only one operand per instruction. If we have this block B2, and we can see that it should split B3, since B3 takes, two of its instructions take the operand from B2, and another instruction takes its operand from B1. So B3 is, it must be split into those which take the operand from B2 and the rest. So in general, what we can see is that we take one block, BI, and compute the inverse of BI, and that's the inverse is the set of instructions which take their operand from BI. Then we compare with each block, and if the intersection is empty, then that other block, BJ, is completely unrelated, so it should not be split due to BI. If it's not empty, the intersection, but BJ is not a subset of the inverse, then BJ must be split. So what we do is to use a work list, and we let each block be the BI, so to speak. That is, each block is given a sword and put on a work list, and it's allowed to cut the other blocks once. Okay, so let's see how this can work out. Again, well, we compute the inverse of B2, and it is FGI, because F, G, and I take their operands from B2. So let's compare if, let's check if B1 should be split. It should not, since this intersection is the empty set. B3 should be split, since, well, as we just saw, it doesn't take all its operands from B2, and the same for B4. The question is now, why should this be faster? Oops, not like that, but instead let's look there. Okay, so if we want to split BJ, and BJ is on the work list, then both parts must have a chance, I mean BJ prime and BJ bis must have a chance to split other blocks. Okay, that why? Well, BJ has not had its chance to split the other blocks, so we cannot just take one of BJ. I mean the parts of BJ. So both must go there. But this is this case. W is the work list. But if BJ is not on the work list, that means it has already used its sort. Then it's sufficient to take only one of its parts to put on the work list. And obviously, it's better to take the smaller one, since that will be less work. Okay, so in this case, we take BJ prime, sorry, bis, to put in the work list. Okay, so why can we do that? Actually, we can use either of BJ bis and BJ prime. If we look at another block, BK, and BK needs to be split due to BJ was split. So BK needs to be split in these two parts. Either BJ prime or bis will create exactly the same splitting of BK. Why? Well, BK will take some of the operands in BJ bis and the others in some other block. That means it will be split as this green shows. Or we do the same and it will also be split as this green shows. So therefore it's better to put the smaller of BJ prime and BJ bis in the work list. And it can be shown that this will result in an n log n algorithm.